Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to introduce Ali Fajardi to Microsoft this morning. He is from UIUC under the advisor of David Forsyth. And his early work was mostly centered on activity recognition. And then more recently, he's done a lot of really great work on attributes and high-level semantic scene understanding. So I think he's going to be talking about that mainly today. So I'll hand it over.
Thank you. First of all, thanks a lot for having me here. It's my great pleasure. So I'm going to talk about better recognition with richer representation. As it sounds, I'm basically going to be focused on representational approaches to recognition and what can we do with these representations. First to talk about, so one, I'm interested in recognition. So obviously it's intellectually very, very challenging problem. It's a core fundamental computer vision problem, of course, and it provides a lot of deep insight to other fundamental problems as well. And I would say even human vision, for example. So, and if you approach computer vision actually correctly, it provides a lot of applications. I don't need to actually explain the applications. Surveillance, robotics, image search, all of those things actually comes as applications of object recognition, assuming that if you approach this problem correctly. The way that we currently do recognition in computer vision community is that we come up with a list of objects that we want to recognize. So we sit down, write a bunch of names, car, bicycle, I don't know, motorbikes, people, and then we actually gather positive, negative examples for those, and then we build models to learn those category models. And then when we want to actually use those models, when an image comes in, we get all of our detectors, run it over the image, and we're just crossing our fingers that one of those detectors are going to be excited about this picture. And said, hey, there's a car in here. I've seen cars before, and it's basically right in there. Most of, or almost all of the focus in computer vision, or computer recognition, or object recognition community is to improve these numbers in these tasks. How can I build a better car detector? How can I build a robust person detector, and so on? We're pushing the bars each year. Each year, you're going to see new benchmarks, new numbers on those benchmarks. And we're basically, we're making a great progress as a recognition community towards this task. But we basically never step back and think about what we're going to do with this recognition system that we're building. What happens if I show you a picture like this and actually run all of my detectors in the picture like this? Should I expect anything out of it? So the best outcome that I can get out of this would be, gee, I don't know what this is because I haven't seen it before. But on the other hand, if I ask you as a human, so what is this picture? You can provide me tons of useful information for this picture. You can say, I don't know what this is, but I'm sure it's vehicle. It has wheel, I can see the wheel. I've seen wheels on other vehicles, so I know this is a wheel. Since it's a wheel, it has a wheel, it's a round thing, it probably moves on the road. And looking at the size of the car, it works with electrical power. So you can infer tons of useful information. You can say it's probably a modern vehicle. If I have to guess, it's probably pricey. So one of my goals actually is to provide such a capability for recognition systems. Without even knowing what this is, human can recognize it, can localize it, localize the wheel, localize the windshield, and provides tons of useful information for this. So part of this talk will be focused on how we can achieve such a capability with our recognition systems. The other actually part is that basically this topic is going to talk about what are the interesting things in the image. The other half would be interested in talking about what is it I'm going to report as the output of my description for an image. Do I want to list everything together and say this is this, this is this, this is this? Or I want to be smarter than that. So the way that we do recognition, or the way that we describe images in the current recognition paradigm is, I'm going to get all of my detectors running all over the image, and that will be my description of the image. List of words. Do we actually really want to do this? Or do we people describe this image like this, or if I show you this picture and ask you, describe this picture, what will you say? You probably select some of those objects. You probably don't talk about the flower back there, the pen down here, the car back there. So you select some of the objects. And then you put them sort of in relationships, in different forms. Maybe in the form of a phrase, maybe in the form of a sentence. So the other part of this talk will be focused on how can I provide such a description for an image instead of listing a bunch of words. How can I select some of those things and put them in relationships in terms of events, actions, functions, scenes, and stuff like that. So basically my talk today would be concerned with 3 big topics. Attributes as a way of generalizing across categories, being able to talk about unfamiliar objects, describing and localizing unfamiliar objects. And then I'm going to go to richer descriptions for images. How can I actually predict sentences for pictures instead of a bunch of words? And then at the end, I'm going to talk about visual phrases, which I'm really excited about, which as a way of getting actually a more sophisticated way of predicting sentences. On the attribute side, I'm going to talk about basically describing and localizing objects. First, I'm going to start with the describing objects, and then I'm going to switch to the localizing part. So my goal of this attribute-based representation is mainly focused on shifting the goal of recognition community from focusing on predicting a single name for an image to learning to describe objects. So basically, my goal is to shift this point of view from pure naming to description. I want to be able to describe things instead of name things or assign a single word to this. And the procedure is a very simple procedure. So an image comes in. There is a little bit of technical detail that I'm going to skip for the sake of time, which is basically try to decolorate attribute predictors and stuff. But at the end of the day, I'm going to have attribute classifiers. I'm going to run it over an image, and then that provides me a description of the object. And if I'm interested in naming the object, I can basically feed a category model to this description, and then find the category. And this description can be semantic attributes or discriminative attributes, so both of them. And I'm going to show, if you adopt this approach, you're going to do amazing new stuff that we couldn't have done before in recognition. For example, not only you can name things as before, this is an airplane, no. You can describe new novel objects, things that you've never observed before. We've never observed carriages before. Sorry. Despite that fact, you can say this thing has wheel, it's made of wood. And a lot of different descriptions. Examples would be, we never observed buildings in our training. But despite that, we can say these things are 3D boxy things which are vertical, and they have rows of windows in it. We've never observed centaurs. Despite that, we can say it has head, it has a leg, we think it has saddle in it for some reason. But we can do more than that. We can also report what's typical or atypical for known categories. Assume we've known birds. We know the properties of the birds. We know birds should have head and beak. If you show a picture like this to a system, it can say, oh, I know it's a bird. But the head and beaks are the head and beak are missing. And that's something that's not usual. And it's worth reporting. I know motorbike. But I don't expect to see cloth on a motorbike. If I see it, I can actually report it. And here are some examples. Basically, we expect to see, for example, jet engine on airplanes. If you don't see a jet engine, you can report it. If you don't see a sail on a boat, that's sort of, the system thinks it's an unusual boat, and it can report it's a boat with no sail. Or the other way around. We don't expect to see faces on buses. And once we see it, we can actually report it. And sometimes we think there is a horn on a bike because the handlebar looks like a horn. And we think it's actually something suspicious. And there's even more than that. So the attribute framework provides you such new functional capabilities that you can do with all of these things. And more than that, you can also learn new categories from much fewer training examples. Or in the extreme case, with 0 visual training example. Like if you assume you haven't ever observed goats before, and I want to explain goat to you. I'm going to say goats are something that has 4 legs. It's some animal that has 4 legs. It's made of wool. It has horn. And basically, I'll list everything for you. So you have some sort of idea about the goat. You're not the best goat expert in the world, but you have some sort of idea about what the goat is with this pure textual description of the goat category. So our system provides such a capability for you to be able to basically learn new categories from fewer or no visual example. So this curve, basically, the dotted black line is the attribute-based framework. The blue line is basically standard recognition. This is the accuracy that we get, and this is number of training examples. So the points that I'm trying to make is, one of them is that you can actually get to the same, sort of the same accuracy with way fewer training examples. Meaning that you can learn new categories much faster with way fewer training examples, adopting this attribute representation. And the interesting part is that what happens if I have 0 training examples with pure textual description of the category? And here's the chance. And here's what we're standing with the attribute-based representation. Still, we're not here because we need basically 40 examples to get there. But with 0 visual example, we can actually go up to here. We have some sort of idea about what the goat is without being a perfect goat expert or a good goat detector. So with that, I'm going to close the description part. So right now, we just talk about how to describe objects in terms of the attributes. And one other thing that we can do, as people can do, is being able to localize unfamiliar objects. Being able to say, this is, I know there's an object here, it's probably a vehicle, here's its wheel, here's a windshield. So we people can do that. Can we ask computer, or can we build a recognition system to actually do the same? And the answer is yes. So again, we're going to adopt the attribute-based, attribute-centric recognition system. We're going to build detectors, not only for basic level categories, as we usually do, but also for superordinate categories, for parts and attributes, for everything. So we're going to have a pool of detectors, and then when a new image comes in, I'm going to run all of my detectors over the image, and each of them are going to have some opinion about where the objects are. And then I'm going to get all of those detections, and I'm going to use all of those detections to reason about the location, the property of the objects. So the procedure looks like an image comes in, I get all of my detectors that I learned on, actually we built a data set called core data set. It's tons of examples with detailed annotations of all of the parts for vehicles and animals. So we use that data set to build the detectors. We get all of our detectors, we run it over an image. Then we have a machinery that actually looks at all of those predictions and decides on where the object is. And then we're going to use this localization information together with all of the detection results to describe the objects. In terms of the attributes, aspectual behavior, functions, like this is carnivorous, this creature can jump. So all of those information. First, how do we localize? So basically, very simple thing, and very fast. Each of the detections have an opinion about where the object is. So the ear detector has an opinion about where the dog is. The nose detector is the same. The dog detector itself has an opinion about where the dog is. The mammal detector has an opinion about where the dog is. The animal detector as well. So we gather all of those votes for the location of the objects, and then we cluster data space, and we pick basically the most populated cluster as the response for where the object is. It's very simple and it's very fast. And once we localize that, we basically can describe the object. The way we describe the object is basically we have two different types of attributes. There are attributes for which we have direct visual evidence. For example, if something has leg, if something is a dog, if something is a mammal. So basically for parts, for basic level categories, and for super categories, we can actually build a detector. So for those things, we have a detector. We have other types of attributes for which we either don't know how to build a detector or it's very hard to build a detector. For example, if some object has the potential of having a leg, no matter if it's visible or not. This is talking about if this thing has a leg or not, it's visible or not. This talks about the potential of the object having a leg. Talking about the functions, this creature can jump, can run fast, is carnivorous. And also the aspectual information is laying down and facing toward the camera. So the way they're going to approach this is we're going to basically learn all of those things by looking at a simple latent roots model. And what it does is basically it tries to look at the correlation of the things that we have detectors for to infer the others. And we solve this, it's very simple EM, we can solve it with EM, and then the inference is exact and very fast. So the gist of the idea is that if I show you a box and tell you there is a head in this side and there is a tail in this side, and ask you which way the animal is facing. People can say it's facing that way. So basically, we're going to look at all of the predictions of all of the things that we have, and the correlation between them to infer things for which we don't have any direct visual evidence. So to see how good is this thing working?
Does the things that we don't have visual evidence for, do they in any way help the detection of the things we do have visual evidence for?
Yes.
So they help weed out the false detections?
No, actually, you're gonna use those as well to marginalize over this.
Okay. So they all help each other?
Yeah, they all help each other. So to actually test this, what we do is we actually get the core data set. We divide it to two sets, familiar categories and unfamiliar categories. So unfamiliar categories are the things that we are not going to observe at all during training. And we're going to see actually can we generalize to those unfamiliar categories or not. The first question is, can I basically learn a wheel model, let's say, on trucks and pickups and cars, and expect this to actually work on motorbikes? And the answer is actually yes. The detectors that we have are actually really powerful. With some loss of accuracy, you can actually learn those detectors. Here's an example. This is learning a leg on the same category and tested on the same category, not the same instance, but instances of the same category. And this is the leg detector, the RC for the leg detector, if you train it on some categories and test it on some other categories. So, and these are examples for leg, horn, wing, head, eye, and so on. So the gist of the idea is that yes, they generalize. They're not as good, but actually they're reasonably good that we can work with them. So here's the sort of things that we can do. So elephant is an example of familiar categories. So we can localize them as before, as a standard recognition system. But we can do much more than that. We can say, hey, this is the animal. It's a four-legged mammal. I know it's an elephant because I've seen it before. Here's the leg, here's the foot, here's the trunk. All of those in localization informations. And things actually get more interesting when we speak. We're shown with an unfamiliar things. We've never observed cats before. Despite that fact, we can actually localize the cat as an animal. Green means animal, red means vehicle in these pictures. And we can say, here's the head, here's the leg. We think it has a hump, and it's a mammal. We've never observed jet skis before. Despite that, we can actually localize them as a watercraft. We've never observed buses before. No single example of bus in our train set. Despite that, we can actually localize the bus and say, I don't know what this is, but whatever this name is, it's a wheeled vehicle. Here's the wheel, here's the license plate. And if you're interested in numbers, basically these are the quantitative results on how good we are on the core data set, comparing to the dotted lines are basically traditional recognition. So what happens if you just focus on basic level detection versus the attribute-centered recognition? So the red curve is for familiar objects. So this is what you get if you adopt the attribute-based representation. Even for familiar case, there is this much gain, considering the attribute-based representation, comparing to only do the standard thing, which is naming. Even for localization of the familiar things. And also there is a gain for unfamiliar, and there is a gain for both of the objects.
So the main reason for this boost, is it because in the standard method, are you using less training data because you're actually generalizing across different categories, so you essentially have more training data, or is it an actual representation that the attributes give you more?
So actually both of them, because you may miss a car, but you may not miss a wheel. Mm-hmm. And then the wheel can actually help boost your car detection in the route model. So basically, in the voting system. So basically, both of the hypotheses are sort of correct. That we get gains both because we have more models, and because of actually those models talk to each other. So far what I talked about, this is an actual results of our system. So we've never observed horses or carriages during training at all. So no single instance of them. Despite that fact, we can say, I know there's a vehicle in here. Here is its wheel, and this vehicle, whatever it is, moves on the road and facing to the right. I know there's an animal here, which probably is a four-legged mammal. Here's the head, here's the leg. This creature can run, can jump, is herbivorous and facing right. So this type of information, you can do this type of inferences for an image by adopting this attribute-based representation. But at this point, I'm going to actually shift the gear and talk about, after talking about what to report, what to predict over an image, talk about what to say for an image. Do I really want to list everything? Or do I want to provide a concise description of an image?
Can you back up a bit? It's going by very, very fast for me.
Okay.
So I think typically we have time in these talks. So I can see that you're detecting a leg, but it's a total mystery what part of the system is saying is herbivorous or can jump or something like that.
So for that, I have to get back to the root model.
Okay.
So basically, this comes from this node that predicts the function of the objects by looking. For example, I want to predict if something can jump or not. I have supervision for all of those things. And what I can do is I can actually learn that if something has a long leg, has 4 of them, and probably has a little belly, they can jump. So we're going to learn those things through the correlation that we're going to learn through the things for which I have a detector. So I'm going to have a detector for leg for all of the parts and the attributes of the objects. And what I can do is I can basically infer things by looking at the patterns of the responses of those detectors.
The notion of a long leg is different than the notion of a short leg?
No, there is no notion of actually long versus short leg at this framework. And if you actually look at the results for things that can jump, for example, can jump, we really think elephants can jump, which they probably can't, because we don't have the notion of weight with respect to the length of the leg, with respect to the muscle power and these stuff. So it does make mistakes because this model is very basically a naive way of modeling these correlations, or the attributes are not detailed enough to infer all of those things. The reason that we can predict some of those things is that some of them, for example, something being carnivorous or herbivorous, it's probably by just some coincidence of the correlations between the things that we have. And so for some of them, basically the correlation is the only thing that helps us to infer that.
So for example, in the example with the cart and the horse, were there other predictions that it made which were not correct? And these all looked...
Sure, yeah. This is actually, I have examples. For example, I showed you a wrong prediction, for example. There is a hump over here. There is 2 trunks over here. So there are many wrong predictions over the image. This is a specific one, which actually we use as an icon of the paper, is actually a perfect example. No mistakes, but it happens.
So facing right for the carriage. If you've never seen a carriage before, how would you infer that it's facing right?
So basically, you can infer it from facing right cars, let's say.
Small wheels in front, big wheels in back.
Exactly.
Or you see the person on top, you see his face.
We don't do that actually. It's just we only look at the information that relates to this vehicle. We don't infer from the person right there. But we can actually. This is to show that if you know how cars are going to be or how buses are going to be facing right, you can actually transfer that knowledge to carriages.
So does that come from the spatial relationship between the wheels and the body of the vehicle?
Yes.
I was a little surprised that none of the attributes were child nodes or had child-parent relationships with the functions. Like I would kind of expect to see that, like, if is herbivore, then that would affect the conditional probabilities of, whether certain things would happen. So they're only communicating through the parent node in the graphical model, which
actually, I agree with that. That you can actually do this child node that makes the model more sophisticated and probably works better. The reason that we didn't do that is that we wanted to have a very fast inference model on exact things, and we wanted to do it fast, or we didn't want to actually get into details of how can I boost those things. But I completely agree with you. If you actually add layers to this root model, you can do better than just with a single layer of the root.
That with only the parent node for communication, that greatly limits how much those nodes can actually move probability back and forth.
Of course, yeah, I agree.
So what are the probability distributions? How do you model the probabilities?
So the distributions for the detector nodes, we basically produce a multinomial. And we're going to consider the other nodes as multinomial, and then we marginalize over everything. So it's basically very simple EM style latent roots model. Okay. So I'm going to go to the second part, which is basically how can I provide a different type of descriptions for images? We think actually sentences would be a right description for images. As I said, so if I ask people, people tend to select some of the objects and then put them in some sort of relationships. We believe that sentences are the right representation for the images. Why? Because first, they provide us with the capability to talk about relationships, events, functions, and also they actually implicitly are talking about what's worth mentioning. If I know how to predict a sentence for an image, I'm basically implicitly sort of selecting some of the detectors and then put them in a sentence. So it's an extremely challenging task for people familiar with recognition. It's very, very, very hard to predict a sentence for an image. If you look at the literature, there are some approaches who are actually trying to do this by being explicit about the relationships. This is on the top of this is below this is beside this, and then they try to do basically to infer those properties. But there's a limit to what you can do with those type of explicit approaches. Why? Because the domain of the problem is very hard. You're gonna be lost in a inference of the very sophisticated models. What we think we should do is we're sort of adopting the nonparametric approach to this problem. By nonparametric, I mean if I have data sets of images and sentences in correspondence, and I have a nice representation, can I actually learn to measure the similarity of a sentence with an image? And if I can do that, then what I can do is, assuming that I have a big enough data sets of images and sentences in correspondence, a new image comes in, I found the closest sentence and reported that as a description. Or a new sentence comes in, I measure the similarity and find the best image. So how can I build that such a similarity score? So what we think is, what we believe that there is this space of meaning in the middle of the space of sentences and images. So each point in this space has a projection into the space of a meaning and has a projection into the space of sentences. So each point here has a projection into a space of images and a space of sentences. So if I can learn these two projections, then I'm home. Basically what I can do is, to score a similarity of a picture, of an image, and a sentence, I project both of them back to the space of a meaning. And then I look at the distance of the projections in that space of meaning. And that provides me a similarity measure. How do I do that? So the way that we're going to do that is basically, since this is an extremely, extremely hard problem, we're gonna have a simplistic approach to this problem. I'm going to assume that the space of the meaning can be represented by an object and an action and a scene. I'm ignoring the subject, object, the properties, the adjective, everything. So I'm just concerned with the object, scenes, and action. And what I'm going to do is I'm going to basically learn this link and this projection discriminatively and together. How basically I'm going to set up a structured learning problem, which I'm not going to talk about. If you're interested, we can actually talk offline. So the job of that structured learning is to basically rank the correct sentence for this image higher than the rest of the sentences. And I'm going to learn the parameters on this space over these three elements of the space of the meanings. To be able to do that, we need a data set put sentences and images in correspondence. So we actually built such a data set called UIEC sentence data set. So we get examples of Pascal. It shouldn't be that dark. Sorry about the picture. And ask people in Mechanical Turk to write sentences over the images. And this is an example of the data set. There are interesting properties of these sentences. So people are, interestingly, are in great agreement about what to say about an image. All of the people are talking about the two men here. All of them are talking about the talking. All of them are talking about the relationship to the plane, and all of them are talking about the plane. So there is this great agreement between people of what to say about an image. They don't talk about the grass back there. They don't talk about the trees, the cloud, the sky, the jacket that this guy is wearing. So people are in great agreement about what to say about an image. And we basically try to implicitly approach this problem because we really don't know how to actually explicitly approach this. It's an extremely challenging problem. It's actually one of my future directions that I'm going to talk about. But if you approach it implicitly in terms of how can I predict a sentence for an image, if I predict a sentence, I'm implicitly selecting some of the things. So basically, the way that we're going to do it is, an image comes in, I'm going to get all of my detectors, all of my scene detectors, all of my object detectors, and all of my action detectors. I'm going to have all of them run over an image. I have a simple CRF that connects these together, and then I'm going to do inference. And then that gets me to, that feeds information to the structured learner. Here's an example of it, of what happens at the end. So, of course, this is not a random example. That's a good example of the method. For this picture, we're predicting a man stands next to a train on a cloudy day. A backpacker stands beside a green train, and different sentences. And remember, we're not generating the sentences. We didn't want to actually get into the details of language generation. We're just getting it out of the data set by just scoring the similar things. And surprisingly, this simple non-parametric approach actually works quite well for images and sentences. We have evaluation metrics in the paper. If you're interested, we can talk about that. I'm not going to bore you with evaluations at this point. And since our system...
Just to be absolutely clear, the sentences that you're generating from this are whole sentences that people wrote down for other images. You're not mixing and matching any parts of the sentence.
No,
you're just taking the entire sentence.
Yes. And since our system is symmetric, what we can do is we can actually go the other way around. If you give me a sentence like this, and remember, this is a sentence written by a Turker. So given that sentence, we can find images like this, a horse being ridden within a fenced area. There are very interesting properties. So for example, we don't have detectors for everything. We don't have detector for fence. We have a limited number of things for which we built a detector. The way that we're going to recognize those is basically, we basically have a way to incorporate distributional semantics to our detectors. For example, if I haven't seen, let's say, beetle. There's a sentence that comes with this. There is a yellow, beautiful beetle in the street. We've never observed beetle, or we don't have a beetle detector. But through distributional semantics, I know beetle is very similar to the car. Beetle is very similar to the bus. It's a little similar to the car, and it's not similar to dinosaurs. So basically, I'm going to reweight my detectors to have a rough and ready beetle detector that I can actually use here. And incorporating those distributional semantics actually works really good. If you're interested about how to incorporate that, we can actually talk about that offline as well. But there is one big problem, as actually Larry mentioned, with this approach, which is what I'm doing at this point is I'm scoring the whole sentence with the whole image. And if I want to do that, I'm basically implicitly assuming that I have a huge data set for which I have sentences that correspond to every possible image, which is a little bit unreasonable assumption. So I cannot build that. And looking back at the history of machine translation, if you look at the history of machine translation, the boost in the machine translation happens when people actually talk about phrases. This chunk of a sentence corresponds to this chunk of a this chunk of a sentence in English corresponds to this chunk of a sentence in French, let's say. So people do translation by phrase. And we have a translation problem. I'm going to translate from the space of the images to the English text. And instead of actually matching the whole sentence to the whole image, at this point I want to actually match the chunk of an image to chunk of a sentence, and then establish a phrasal recognition basically system. That gets me to this third part of my talk, which is how can I learn complex composites, like a person riding a horse, or a rider and a horse jumping over a fence. How can I do that? Because if I can learn those, basically I sort of learned a phrase detector, which basically has something which is bigger than an object, but smaller than a scene. So we always talked about objects and scenes. And we never thought about actually there might be something in the middle. And those phrases are something that's in the middle. So they are bigger than an object that corresponds to the chunk of an image, bigger than an object, but smaller than the whole image. Similar to the phrasal translation, their phrases consist of a couple of words or more than words, but are smaller than the whole sentence. How can I do that? So conventional wisdom in vision says, if you want to detect a person riding a horse, detect the person, detect the horse, and then sort of put them in correspondence somehow. An example of that would be the Devos paper on how to basically learn this is on the top of that, and this is beside this, and therefore infer that this is a person riding a horse. When we do that, we're implicitly making a huge assumption which is wrong. That assumption is that the appearance of the objects are going to be the same when they interact. But as a matter of fact, the appearance of the objects are going to change a lot when they participate in relationships. A person riding a horse takes a very few characteristic postures comparing to a typical person. A horse being ridden by a person actually is quite different from a typical horse. A person drinking from bottle has actually such a rigid characteristic behavior comparing to a typical person that we actually are suggesting that if you want to detect these things, why don't you detect it as a whole? If you want to detect a person lying on a sofa, you're going to have a miserable time detect the person, detect the sofa. But these things together provide such a reduced visual complexity that you can actually learn them as one entity. So we are proposing, instead of learning horse, dog, besides learning horse and dog, what about learning actually person riding a horse? A dog lying on a sofa. What's wrong with this? The first thing that comes into mind is that, well, I have a combinatorial number of phrases that I can make out of words. How are we going to deal with that? Do you want to learn a combinatorial number of phrases? And if you want to do that, I'm sure you're not going to have enough training data to do that. And the answer is actually, it's very similar to what happens in language. So there is a saying that you can generate, with the amount of words that you know, you can talk your whole life without repeating a phrase twice. But we people don't do that. We actually have very few number of frequent phrases that we use a lot. And what we're proposing is that there are few very characteristic phrases that we can highly reliably detect. And there is no excuse on not using them and not getting them into our recognition systems. Our recognition system consists only of objects before. Some people talk about context and scenes and stuff like that. And we're actually adding these phrases to it. Why? Because they're very characteristic. We can actually learn them very, very reliably. And they're much better than learning the individuals apart. How am I going to do that? Basically, we built a phrase data set called Fraser Recognition. It consists, we get basically objects from Pascal, the objects that really know how to deal with them. They're famous objects from Pascal. And then we basically make all possible phrases that we could think of out of those objects. And we add up, basically there are 8 objects, 17 visual phrases, almost 3,000 images. And we draw bounding boxes for all of the phrases and all of the objects in them. Because of this great reduction in the, look at the people drinking from bottle, for example. Look at the people riding horses. So there's this great reduction in the visual complexity of the objects, that what I can do is, basically I can learn a detector directly for those. And surprisingly, I don't actually need so many examples to do that, because it's such an easy detection example. It's very characteristic. For example, if I show you this picture and ask you, what does this correspond to? You probably can say it's a person riding a horse. What's the model for this?
Bicycle.
Exactly. So it's so simple. The behaviors have such a great characteristic that we can easily learn detectors for all of those things.
Yeah, I have a question about the 17. So when you say 17 phrases, do you mean 17 pieces that can be recombined into other phrases, or do you mean 17 explicit phrases like a person drinking from a bottle?
The second.
Okay.
So 17 person riding a horse, person jumping on.
But I mean, even if you argue that, you could argue that the space of all possible phrases is combinatorially huge, and there's a lot of repeat, but 17 is small with respect to,
yeah.
I mean, do you...
So actually learning these, scaling these to hundreds or thousands is easy, because actually I only learned 50 examples of those. So these are so easy to train and so fast to train that you can actually learn them very easily. Later on, actually, I'm going to show you some experiments that totally convince you that it's not a scale issue in this subject. Let's see the models in action. So here, these are basically the comparison of person riding a bicycle, person and bicycle detector. Bicycle detector has absolutely no clue about the bicycle. There is only one person detection over here, whereas the person riding bicycle detector actually fires in 5 correct places. The dog detector has no idea about what's going on over here. The sofa detector has no idea. But the dog lying on a sofa actually finds it. The bottle detector has no idea over here. But the person drinking from bottle actually fires over there. So the next question is actually, how can I compare this approach, which is basically train the phrases directly, versus find the individual components and then put them in correspondence. For that, we actually built a baseline. So what this baseline is trying to do is that it tries to basically find an upper bound an optimistic upper bound on how well one can predict a person riding a horse from this prediction of a person and this prediction of a horse. And we're actually building a very, very generous baseline. Well, how? Basically, I'm going to extend the bounding boxes to form another bounding box. And I'm going to use the min, the max, and the mean of those confidences to basically put on the final bounding box. But I'm not going to stop here. I'm also going to regress the position of these two bounding boxes. I'm going to regress the position of the final bounding box against these two bounding boxes on the test set. And I'm going to regress the position and the confidence over here. And I'm going to look at all of those things, and I'm going to pick the best one on the test set. So this is an extremely generous baseline. I'm just saying that what is an upper bound on how well one can predict this phrase from those predictions. And I'm going to basically train my regressor on the test set. And I'm going to compare this generous baseline to detection the phrase as a whole. So these curves are RC curves. The blue lines are detections for the phrases, and the red one is the baseline that I just talked about. Look at the huge gaps. These are not actually easy to get gaps in recognition. If you look at the recognition results, they're just tiny little gaps on RC curves.
So how did you train the baseline here? Did you train it on the same images that you trained yours on, or did you train it on generic people?
So for those, we actually have two things. I use the state-of-the-art person detector that Pedro gets out of the Pascal. Yeah. And I have a person detector on my own data set. Okay. I'm going to run both of them, and I'll pick the best one. Okay. So basically, this one is basically modeling the best possible detection plus the best possible relationships. The problem is that a typical person detector won't get a person riding a bicycle because it's bent. And if you want to build a roots model that actually handles all the variations of the people, the root model is going to be lost.
I mean, it might be a function of the training data because you're training the people on these very diverse people images, which have very few people riding on bike images. In a lot of ways, this looks similar to the component models of Pedro's, where basically they take people and they break that data set into, let's say, 6 or 10 different possible components. You know, people laying down, people standing up, people cut off at the waist, that sort of thing. And you're basically saying, well, let's do another cut, which is people on bikes.
Sure.
You know, so what's
basically, you're asking two questions. One is, do you train this on a biased data sets that people are actually on the box only? The answer is no. I basically trained two detectors per person. One is on the Pascal, state-of-the-art Pascal detector. The other is trained on my own data set. Okay. So basically, I'm trying to capture both of them. And as a response to the second one, look at this curve. So if the root model can handle that, this curve shouldn't be here. There should be somewhere close to that, or there should be a smaller gap here. The reason that actually the Pedro's model cannot do that is because the variation is too big. You cannot have a latent root model with 20 different latent roots, and you can expect that to actually do these things. And those gaps are actually amazing gaps. Look at, I don't know, horse and rider jumping. So you usually don't see such RC curves in vision. I haven't seen this one before. A person drinking from bottle. So it's basically, we have not much idea about the bottle because we don't get the bottle right, and then most of the time the persons are confused. So these are the proofs of actually if you learn those detectors together, because of this very, very rigid visual structure of the phrases, you're going to have a very, very easy time to learn a very, very reliable detectors for the phrases.
Okay, so maybe another way to phrase this is, what if you took both of them learned from the same training data set, right? Both of them, let's say people drinking a bottle, a person drinking a bottle, right? So we show the baseline and your method both the exact same data set. The only difference is when you show your person drinking bottles, you have the bounding box around the person and the bottle, whereas like with Pedro's, you actually draw a bounding box around the bottle and around the person.
Then you have the baseline, basically.
Yeah, that's your baseline. So is that what you did for the baseline, or is that?
Yes. So
that is.
So basically, this is a way of predicting the final phrase bounding box out of a person and a horse.
Well, you did this on the training. When you actually trained the models, you trained it with the same.
For the baseline.
For the baseline.
Yes, and I trained it on the test set, not on the train set. So basically, I trained this to predict the position of the phrase from the position of the components, and the confidence of the phrase from the confidence of the components. And then I'm trained it on a test set, basically. And this is what you get. So now that we have this amazing results for basically detecting phrases, what should I do with this? Am I making the problem even harder than what it was? Because we had objects before, and we didn't know what to say about the image. Now we are having objects and phrases, and I can run all of them over an image. What can I say about it at the end of the day? And we believe that there should be a decoding machinery in every multi-class object detection system, like machine translation, that sits on the top of the predictions and decides on what to say about the image at the end of the day. So your image comes in, you run all of your objects, phrases, whatever detector. Each of them has an opinion about where the objects are, where the phrases are. And if I show you this and ask you, okay, what should I say at the end of the day? Maybe there is a weak horse detection right in here, which is just right below the threshold and didn't make it through the final answer. Maybe these are actually a little bit over the threshold, and by just pushing them down, I can get rid of them. So there is a machinery that we actually developed a machinery called decoding machinery that sits on the top of those predictions. And what it does is says, okay, if there is a person riding a horse over here, there is a person over here, there should be a horse prediction somewhere down there. So let's push that prediction up. Let's push this horse prediction up. Let's push those things down. And basically the decoding machinery sits on the top of all of those predictions and decides what to say at the end of the day about the image. Decoding is not a new thing in actual object recognition. We always do decoding. Non-max operation is one way of decoding. It's an A way of decoding, saying that if this bounding box overlap with this bounding box, get the best one and then ignore the rest. But usually the way that we're going to phrase our decoding problem is, so we have bounding boxes. Let's say I have 3 different categories, red, blue, and yellow. And I'm going to run all of those images. I'm going to phrase my decoding problem as assigning zeros and ones to these bounding boxes, so that I'm going to basically mimic my training set. Or if you don't like to make the hard decision at the beginning, you can phrase it as I want to increase the confidence of some of those and decrease the confidence of the others. So if I ask you immediately model this problem, what you typically say is it's basically a unary plus binary approach. The unary term talks about the appearance of the bounding box. The binary term talks about the relationships. So that's a typical way of doing this. But there are problems actually for which we really don't need to get to do this hard inference to be able actually to do this task that we want to do. Sometimes if you're smart about representations, we can avoid solving the hard problem. So what we can do here is we actually ignore this binary term that talks about this is beside this, because you cannot model it correctly. You end up with greedy inferences, and then the results are not going to be as good. So we're going to model these pairwise relationships in the feature representations of the unaries. As a result, we have a simple inference, which is basically a unary term, and we're going to ignore the binary term. We're going to basically put all of the binary informations in the unary term. How? So basically, let's assume I want to represent the thick box over here. What I can do is I'm going to build a long feature vector that has very crude spatial bins above, besides, and below. And for each of those bins, I'm going to report the max responses of all of those category responses and put it over here. Then if I show this to my learner at the end of the day, my learner has an idea about the local context. If this corresponds to the horse, if this box corresponds to a person riding a horse, there should be a strong response for a person on the above bin. There should be a strong response for the horse in the middle bin, and maybe there is a fence in the bottom bin. So basically, by designing this feature, I'm avoiding having the problem of solving this inference and turning the problem to a simple inference. So the problem formulation is that I'm going to predict an H, which is the assignments of ones and zeros to these bounding boxes. And I'm going to phrase it again as a famous structural learning problem. So I'm looking for the W's to assign to my features, so that the ground truth hypothesis scores highest compared to the other problems. And then we have a combinatorial search here, which actually deals with this maximization problem. Let's see some of the decoding results. So there is a person riding a bicycle over there, and there are 3 wrong person detectors. So the person riding bicycle actually pushed up the bicycle and pushed down all of the wrong persons. There is a dog lying on the sofa here, which is very confident. So the dog lying sofa got rid of all of those person detections and pushed up the sofa prediction up. Why? Because if there is a sofa over there, if there is a dog lying on a sofa, there should be a sofa nearby on the besides bin. So you just look for the highest weak prediction, which is below threshold, and just bring it up. If you like numbers, so we compare. So one thing I would compare is how good you can predict objects using phrases. Basically, phrasal recognition not only is good by itself, but it's also good in boosting object recognition. So these are the state-of-the-art detection responses on those 8 object categories that we're dealing with. And these are our final results. If you are in recognition business, you know that from this to this, it's a long way. So if you look at the numbers in Pascal, it's basically there are tiny little bit improvements on APs. And these are basically, some of them are huge improvements in terms of APs. To compare this with if phrases are helping or not, actually we're going to run our thing without our decoding, without the phrases. And as you can see, the numbers are actually going down. Meaning that phrasal recognition actually helps object recognition. If you include phrases which are reliable, very easy to detect, into your recognition machinery, into your recognition spectrum, you can actually boost your recognition results. And also, it also matters how to decode. If you do the hard way of decoding it, if you do it like with the unary plus binary and then stuck with the greedy search, you're not going to do as well. So these are the state of the results with those modeling, with and without phrases. And what this actually shows you is actually it matters how to decode. If you're careful about your problems, some of the problems do not necessarily need a CRFE type thing, that you actually have to model the relationships. And being careful about those actually matters. To conclude, so I talk about issues with recognition. I personally believe that there are serious problems with the way that we think about recognition. And I think we have to rethink recognition. And basically, one of the conclusions, the attribute story, the visual phrases, are different ways of rethinking about recognition. I believe we have very powerful machineries, but we have to be careful about how to use them. So in attribute story, we didn't basically build a new machinery. We just used the classifiers that we had before. Or in the phrases story, we didn't build a new detector for phrases. We just used the powerful detectors that we have. But we have to be careful about how to use them. And sometimes, like the decoding story, we have to build new machineries to be able to do your stuff. And basically the theme of my research is that representation is the key. So if you get the representation right, the rest will follow. And that would be basically the gist of all of the things that I've done. In terms of what I plan to do next, basically my short-term goals are, the first one is I would like to answer the question of what is the right quantum of recognition. From the day that we start recognition, we always thought, okay, there are cats and dogs and bicycles and cars, and we want to detect them. Let's go and detect them. And then we're beating our detectors to produce best results on those fixed categories. Why? Why should only actually deal with basic level categories? Why not actually including phrases? Maybe there's something else between them. So basically there's this spectrum. There are objects, there are phrases, there are scenes. And we believe that these phrases actually sits in between the scenes and objects. There might be some other things. So I'm trying to find a principled way of finding out what is the right quantum of recognition. And I don't believe that the categories that we have right now is the right way of doing recognition. The second thing that I want to do is kind of related to this, is that I want to break down this notion of categories. So we want to build a dog detector. The way that we do is that we have examples of the dogs, and then we have the models. The best one is basically the Pedro's model, the root model. So we're going to beat that model to be able to detect dogs in different poses, in different aspects, sitting dog, standing dog, jumping dog. And then we're going to basically have models that we cannot manage at the end of the day. So what I want to do is I want to break these strong walls between categories. maybe I can build a reliable detector that can get half of a dogs and half of a cats and half of a horses. Well, it's very reliable. Why not using that and then build a model on the top of that that can use those informations? So basically, this topic tries to attack this convention that we have in recognition, that we want to recognize objects. These are cats, these are dogs, these are bicycles. Let's recognize them. So I'm going to break this in here. And the third thing that I want to do in short-term, near future is to build a phrase table. So what we have right now is a machinery to get the phrases right. And I believe we also have a machinery to get regions out of images. And those regions are not necessarily superpixels or segmentation. Those are regions that correspond to high objective regions. So we can couple that with our phrase recognition, and we can build a big table that has regions of the image on this side and phrases on the other side. So I know there is a person riding a horse that corresponds to this and this and this region, and not to the rest of the region. And very similar to machine translation, we can have a decoding that looks at this big phrase table, that has regions over here, phrases over here, and produce a actually description for the image. But our decoding is quite different from machine translation decoding. Why? Because we have to take care of inclusion, exclusion. Two things cannot belong to the same thing. So we have to have a decoding that's different from machine translation decoding slightly. But I believe actually if I do this phrase table, then we can produce statements of the objects much richer than the list of the objects and more accurate than the way that we do recognition now. For future directions, these are basically sort of a long-term goals. I plan to be able to reason in semantic spectrums. So we have parts, we have attributes, we have poselets, we have objects, we have phrases, we have scenes. There might be some other things in the middle. I really like to be able to reason in this semantic spectrum, to be able to talk about, to infer all of those things. And this is not necessarily a top-down or a bottom-down approach. So maybe a strong part detection can help a poset detection, can have object recognition. Or a strong phrase recognition can actually help a part detection as well. So the other topic that I want to talk about is basically getting the geometry in. So with the advent of all of those nice methods like the Varshall's work that you guys are probably familiar with, that you can fit boxes to the rooms, you can actually infer you can actually couple that geometry with a lot of different things. You can couple geometry with material recognition, you can couple geometry with object recognition, with affordances, and all of those things. And you can actually put them in a nice unified framework. The last thing that I'm going to talk about is about knowledge selection. As I said, we people are actually really good in selecting what to talk about and what not to talk about. If you want to describe this picture, you probably don't talk about the whiteboard back then, or you probably don't talk about the letters over here. So we're really good on selecting what to say about, what to talk about. And one of my goals is actually to basically learn to select knowledge the way that we do. Why? Because that basically simplified many applications, for example, image search. Because then we know what our reports are sort of aligned with what people think, and then that makes the search much easier. The things that I didn't talk about, if you're interested in, we can talk about in meetings. I've worked on knowledge transfer and split-based representations based on comparative representations. If you're interested in that, we can talk about it. There's some work on scene discovery and multitask learning. There's a work that joins multitask learning with manifold learning, if you're interested. Sign language and human activity recognition stuff, and a little bit of work on using machine learning approach to do wide spectrum measurements to ensure network security. And with that, I actually close. Thank you.
I have one question. It seems like the phrases, kind of the main take-home message is that the data term, the appearance of objects, is not independent of the relationship. But we need to take into account the relationships of objects when we model their appearances. Is that?
So there are different things you can actually take as a take-home message. One is that the appearance of the objects changes dramatically when they participate in relationships. And if you ignore that, it hurts a lot. I show you the pictures. The other thing is that I want to basically break down this tradition of having objects as the quantum of recognition. There might be some other things which are extremely useful and extremely reliable to detect. And I want to introduce them to the vocabulary of the recognition. And the second point is actually more important than the first point, which is the selection of the quantums of recognition at this point is almost arbitrary. And I believe there should be a principled way of doing it. One principled way is basically think about phrases, relationships. Maybe there are other principled ways. Maybe there are other quantums other than phrases and scenes that we don't know actually and appear later.
Figure one more time.